is the output, will be equal to G1 times U1 plus G2 times U2. Okay? Or if you have a negative sign in the summation here, then Ys will be equal to G1 times U1 minus G2 times U2. Okay? If you have a minus sign in the summation here. All right? Okay, this is the additive property of the transfer function. If you have a transfer function which is in series, like figure 4.3, then y2 will be equal to g2 times y1, and y1 will be equal to g1 times u, or y2 over u will be equal to g1 times g2. Okay, so this is what you can see from equation 448. All right. Now, example 4.6. The dynamic model of stir tank heating process with constant volume in equation 236 is something like this. Okay, equation 2.36, something like this, and then we put the values of W, C, rho, V, and then we try to find the T bar. We will get the T bar at steady state will be 100 degrees Fahrenheit. Okay. Inlet temperature is changed from 70 to 90 at times equals to 0. And the heater input Q is changed from 1620 to 1600 BTU per minute. Derive a transfer function model for this system. So we go to here, and this is the steady state. Steady state, you can see that the rate of accumulation should be 0. So we can find the value of the steady states of all variables. So you have Q bar will be equal to WC T bar minus TI bar, right? And we already know that. And then introduce deviation variables by subtracting equation 449 from equation 236, and noting that dt is equal to dt prime dt, and you will get this one. Okay, or you will get this one, which is the same, almost the same like equation 236, right? Instead, that this equation 451 will be in deviation variables, okay? While this one, equation 236, in the real variable, right? And we will get rearranging gives the desired transfer function model, that is T prime will be equal to K2 over tau S plus 1 Q prime plus K1 over tau S plus 1 Ti prime. Okay, where tau is equal to rho V over W, K1 is equal to 1, K2 is equal to 1 over WC. Okay, okay, from here, and then goes to here. Okay, of course you can do that because from here to here you just divide this function with by rho V rho C, right, over here. So you will get rho VW over here, and you will get K1 is equal to 1, and K1 is equal to 1, and K2 will be equal to 1 over WC. Okay. Any questions? No? Now, for the input changes at t equals to 0, of course, we are going to use deviation variables. So from 70 degrees into 90 degrees, so we have 20 over s, and q prime s is 1600. If we look at this one, Q is changed from 1620 to 1600. Oh, wow, this is not the same. So this must be wrong. Instead, 1620 should be 1920, according to this. Do you agree?
Yes, sir.
Okay. Okay, can you see that? Okay, so this is not 1620 then. This should be 1920 to 1600. Okay, so we will have a negative sign, okay, minus 320 over s. And then when substituting in equation 453, we will get something like this. And then after simplification, you should check in the table of Laplace. You will get something like this one. And the result will be t prime is equal to 15 over s times 0.5 s plus 1. So the corresponding time domain solution is this one. Okay, as you can see, you should put back the variables, the real variables. Okay, so uh, don't stop just only in the deviation variables, but you put it back into real variables. In this case, so it will be t is equal to 100 plus 15, 1 minus e to the minus 2t. Okay, any questions? No? Since there is
No,
no
sir.
question,
Yes, sir. No question.
okay, so I assume that you understand what we have discussed. So let me continue with the example 4.7. Example 4.7. Now you have two uh, tanks in series. Okay, we are talking about the liquid level in tank. Okay, so we have H1 as the liquid level here, and H2, okay, for the first tank and the second tank. Okay, so and we have the resistance R1, we have the flow out from tank 1, which is Q1, and here we have the resistance of R2 with the flow rate, effluent flow rate of Q2. Okay. Okay. If an exit flow rate is proportional to liquid level or head in that tank, derive the transfer function that relates changes in the exit flow rate Q2 of the lower tank to changes in the inlet flow rate to the top tank Qi. So the question is, what is the transfer function between Q2 and Qi? Okay. All right. What we should do is first try to find the transfer function for the first tank. Okay. And we already learned that this will be a first order uh, system, right? First order process. Okay. Where we have found the answer to be, let me see, answer of h1 prime over qi prime is equal to r1 over a1 r1 s plus 1, which is k1 over tau 1 s plus 1. Okay, can you see that? Okay, see, if we trace from this equation, okay, from the mass balance equation, you end up with this equation 460, right? So you have something like this, and then you collect the h1 prime in the left hand side, and you will have that h1 over q1 prime will be equal to r1 over a1 r1 s plus 1 or k1 over tau 1 s plus 1. Okay, can you see that?
Yes, sir.
Okay, now suppose I want to find, rather than h1 prime over q1 qi prime, how about q1 over qi? How about q1 over qi? So what do you think? If I want to find the transfer function between q1 over qi, okay, then q1 over qi is equal to q1 over h1 times h1 over qi. Okay, do you agree? Let me write in the let's see, where can I write that? I would like to use the whiteboard. Oh my goodness. How can I use the whiteboard? I forgot. Share screen. Maybe from, okay, share screen. All right, so I will have, I should use the pen. If I want to find the transfer function between Q, my goodness, how come? Q prime over Q I prime, this will be equal to Q prime over H prime times H prime over QI prime. Do you agree?
Yes, sir.
This one is equal to QI over H1. If you look at the equation, then it will be equal to 1 over R1, right? And the H1 is R1 over A1 R1 S plus 1. Okay, And this will be equal to, because this can be crossed out, so I will have only 1 over A1 R1S plus 1, which is 1 over tau 1S plus 1. Okay? Do you agree? Okay. So if you want to find the transfer function between variables, what you have to do is just you try to multiply, one transfer function with the other transfer function. Okay. So you will get the answer. Okay. Any questions? No?
No, sir.
Okay. Now let's go back to the verb here. Here is Qi, Q1 prime over H1 prime is 1 over R1 will be equal to 1 over K1, and therefore Q1 prime over Qi prime will be equal to Q1 prime over H1 prime times H1 prime over Qi prime. So it will be 1 over K1 times K1 over tau 1S plus 1, which is 1 over tau 1S plus 1. Okay. The same procedure leads to the corresponding transfer functions for tank 2. Okay. So if we want to find the transfer function between Q2 prime over Qi prime, you will have something like this. Okay, equation 469. All right. Okay. Remember, because this is the flow rate and this is the flow rate, it could be that this is the numerator will be equal to 1. Okay, because they have the same velocity. Okay. And now for two tanks in series, we will have a second order transfer function because the polynomial for the denominator has the power of 2. Okay, right? Because this can be uh, written as tau 1 tau 2 s squared plus tau 1 plus tau 2 s times s plus 1. Okay, which is a second order transfer function. And now for the block diagram, we can write something like this one. Okay, Qi prime, the input and the output is H1 prime. So this is a transfer function between Q1 prime and H1 prime is this transfer function between H2 over Q1 prime. This is the transfer function between H2 prime and Q2 prime. This is the transfer function. And we multiply those transfer functions one. So if we want to use Laplace transform, then we will have to linearize this. Okay, so suppose dy dt is a function of y and u. Okay, so what we have to do is to linearize this function first. If we linearize this function, then this should be written as function y, and u is equal to a function y bar at y bar and u bar plus the differential of the function with respect to y at y bar and u bar times y minus y bar plus the f du at y bar u bar times u minus u bar. Okay, so we have to linearize this. Okay, now if we linearize this derivative will be a constant, and you have the function in what, in a linear function, because the y here has the power of 1, and also with the u also has the power of 1. So this is a linear function now, okay, where this one is a constant, right? Because you evaluate the function at a steady state condition. All right, and then we can try to apply that rule into this one. Example 4.8. Consider a single tank liquid level system where the outflow passes through a valve. Assume that we have this valve discharge rate is related to the square root of liquid level, something like this. Okay, where CV depends on the size of the valve. Derive an approximate dynamic model for this process by linearization and compare with the results in example 4.1. Okay, now we have the mass balance like this, right? And then we have to linearize CV square root of H, okay? And when we linearize that, we will have the linearized differential equation to be something like this one, okay? This is in the deviation variables, all right? Any questions? So what you have to do from this one, equation 475, you put, you write A dH dt Qi minus Cv square root of H. You change this Cv square root of H according to this, from this equation, okay? I think you have problem to once again. I have oh, A dH dt is equal to Qi minus Cv square root of H, right? You agree?
Yes, sir.
And Cv square root of H is Cv H. I don't use symbol square root, but put like this. Okay, bar in here, right? Plus the differential of H, now the function with respect to H. I have Cv times what? Minus half H bar, right? Times H minus H bar. Do you agree? This is dot. Okay, so I will get Cv h bar minus h plus this one I will put into 1 over r rv, for example, and h minus h bar. Okay, where 1 over rv is equal to cv times minus half times h bar. Okay, did I do something wrong here? The differential of h to the power of half is, oh, maybe I'm wrong here. Half, h to the half is this one, half minus half, right? Do you agree? Come on, try to differentiate h with respect to h square. H square,
H square will be 2, differential will be 2h then. So this will be h raised to the power minus 1 over 2 minus 1 will be minus 3 over 2.
this will be h to the half, right?
Yes, sir.
So if you differentiate h to the power of half, will be half
Half
h
h
minus.
minus, yeah, minus 1 over 2. Oh, okay. 1 over 2. Okay.
Do you agree?
Yes, sir, yes, sir, yes, sir.
Okay. Now, if we agree with that, then at,
But please, sir, this part, the CV plus the 1 over 2 h minus that the second part.
let's wait a minute. I made a mistake here. H to the half, so not minus but plus
Okay.
here first,
Oh,
right?
yes, sir.
Yeah. Now, what your question?
If that is it, now it's okay. Now it's okay.
It's okay.
Yeah.
Good. All right. Now you can use this as 0 here at steady state. Oh no, before steady state. I should put still dHdt. As I told you before, I should put this into Qi minus this one, right? Oh my goodness, why? What happened to this? Low battery. See, oh my goodness. CVH half plus 1 over RV. I just put this like that. Okay. 0 is equal to Qi bar minus what? Minus CVH here. Bar half, right? Okay. And then I will have A dH dt d prime is equal to Qi prime minus 1 over RVH prime, right? Okay. Do you agree?
Why 1/r is not linear with the CVH?
Which
Above?
one? This one?
The last, oh, the last sentences.
Last sentence. Which one? This
Oh,
one?
last equation. Yes, yes.
Yeah.
Why it is not replaced on the above? Sorry, can I have a annotation? I mean, like, why minus 1/RV? It is not like linearly with the CVH above the 1/RV.
Oh, he mean why zero is equal to K A minus CVH exponent minus 1/2. The mean why said did not add the minus 1/RVH prime over there at the top. He's asking why it is not.
Wait. Okay. This equation, do you agree or not with this equation? Second equation here. Do you agree?
Yes, that one.
Yeah, we agree.
You agree? Okay. At steady state, this will be 0.
Yes,
This
sir.
will be QI at bar.
Yes,
This
sir.
will be CVH minus half at bar. But this part will be 0 because H prime is 0 at time equals to 0. Right?
Oh, yeah.
Oh,
Oh, okay.
Okay.
Thank you, sir.
okay.
Okay. So that's why when you subtract this, you will get this one only because this one is 0. All right.
Okay, sir. But sir, please, why is it now H exponent minus half? Supposed to be half.
This one H bar,
Oh,
not minus.
okay. I thought it's minus. Okay. Okay. All right.
Yeah. Maybe I'm wrong here because actually this is the bar. H
Not
bar.
minus. Okay.
There is H bar. Okay.
Okay.
H bar means H at steady state. Okay.
Okay.
And then you just follow the regular way as before. Okay. I mean, set H prime here into on the left hand side, and then this will be still QI prime, and then you Laplace transform them, and you will get the same as in the textbook. Okay. Okay, I'll go back to there. Wait here and then come here. All right. So this is what happened where here, right? Just exactly as in the equation 478 that I told you before. All right, and then that's it. You will get the answer the same. All right, now we see example 4.9, state blending system. We have something like this before. Okay, this is the mass balance, and this is the component mass balance. Remember that? And then we have to linearize this. Why we have to linearize this? Because that the input variables now W1, W2, and X1 is not a constant, but it's a variable. So if we go back to the equation here, if we back to the equation here, we have W1 is not a constant now. X1 is not a constant now. So you have a multiplication of two variables, W1 and X1. Okay, so this is a non-linear function. Okay, because you multiply one variable with other variables. So that's what we call non-linear function. Okay, so you have W1 X1 and W2 and X, right? Because you have here plus W2 X2 minus W2 X. Okay, X is not constant and W2 is not a constant, so this is also a nonlinear function. So you have to linearize this. Okay, now if when you see the example with the liquid level, it's just only one variable, right? You differentiate the variable of H, right? But here you have to differentiate two variables, one with respect to W1, the other with respect to X1. Also the same thing in here for W2 times X. Therefore, Seaborg said, look, you have to differentiate something like this one. Okay, so rho v dx dt, rho v dx prime dt is equal to df dx x minus x bar plus df dx1 x1 minus x1 bar plus df dw1 at w1 minus w1 bar df dw2 as w2 minus w2 bar. Okay, so there are two functions. Okay, and then partial derivative at steady state, you have to derive that, so it will be minus w1 and minus w2. Okay, can you see why you have this function? Sorry, this is a constant. Okay, look back at the equation. Okay, and df dx1 is w1, df df, oh, this should be dw1 will be equal to x1 bar minus x bar, and df dw2 as will be x2 bar minus x bar, which is 1 minus x. Okay, any questions? Any questions? No?
No.
Okay. And therefore, you will have this from non-linear equation, you will have linear equation now. Okay. You have linear equation. Now you are ready to Laplace transform this equation because now this equation is linear. Okay. And when you do that, you will have the Laplace transform of x prime s will be equal to k1 over tau s plus 1, x1 prime plus k2 over tau s plus 1, w2 prime plus k3 over tau s plus 1, w1 prime. Okay, three input output transfer function can be derived from step 6 and 7. So when you want to find individual transfer function, what you have to do is make this function is input equals 0. Okay, so in order to get x prime over x1 prime, put this into 0. Okay, so that's why you only have k1 over tau s plus 1. Okay, And to find x prime plus w prime, you put something like this, k1 over tau s plus 1. Okay, so you put this 0 and this is you put 0, right? And also the same is true for to find x prime over w1 prime. Okay, now when you add it together, so you have x1 times g1 x1 prime, you have x prime is equal to g2 times w2 prime, right? And then you have x prime as is equal to g3 times w1 prime. Okay, when you add together the this transfer function, then adding this transfer function will be like this. Okay, not it becomes 3x prime s will be equal to this one. Okay, so it's different when we add the transfer function, then you will have something like this. Okay, not you add one by one like that. Okay, so this is how to deal with the transfer function. Okay, now a little bit more complex here, more complicated, where we have a CSTR, right? Continuous stir tank reactor. We assume it is a single first order chemical reaction. Then we will have the mass balance, something like this, equation 266. And this is the energy balance, equation 268. Okay, where the reaction rate coefficient K is given by the Arrhenius equation. K is equal to Q0 e to the minus e over RT. And we know already that this will be nonlinear. Why was that? Because we have K over here. This is a variable now. And we have CA is also a variable, right? So this is a nonlinear function. So we have to linearize this, okay? And when we linearize this, you will get equation 488 and 489, okay? And then from there, you can find now the transfer function between CA prime over TC prime, which is something like this, okay? Now, remember, I told you before, if a system should be physically realizable, then the power of S in the numerator should be less than or equal to the power of S in the denominator. Okay, and we can see in the denominator the power of S is 2 and the power of S in the numerator is equal to 0. Okay, because this is a constant, right? So we can say that this transfer function can be physically realizable. Okay, so this is the model of a CSTR. Okay, suppose you have a CSTR and you got the model where the numerator has the power of S greater than S in the denominator, then the model that you have is wrong. Okay, so be careful when you want to try to find the model for a physical system, then this power polynomial in the numerator has to be less than or equal to the power of S in the denominator. Okay, understand? All right, so that's finished for chapter 4. And maybe we have still the time to check with the answer in chapter 3. Right? Um, Rizky Aulia Lara. Is there Rizky Aulia Lara?
Yes, sir.
Okay. Can you explain to us about the assignment and the short quiz that you have?
Okay, sir.
Amanda, please give Rizky. All right.
Excuse me, sir. The share screen is still disabled.
No, I think I already stopped the screen. Now Amanda or Yao can give you the right to show in the screen.
Try again. Try
Now
again.
you can share, Laras.
So what happens, Amanda?
Now Laras can share, sir. The share screen is already open for all.
Okay. Uh, can all of you see the share screen?
Yes,
Yeah.
Laras.
Okay. So this is the question of 3.18. A continuous stirred tank reactor is initially full of water with the inlet and exit volumetric flow rate of water having the same numerical value. At the particular time, an operator sets off the water flow and adds caustic solution at the same volumetric flow rate V, but with concentration C. If the liquid volume V is constant, the dynamic model for this process is like this equation, where Ct is the exit concentration. Calculate Ct and plot it as a function of time. There is a data where V equal to meter cubic, Q equal 0.4 meter cubic per minute, C equal 50 kilogram per meter cubic. So this is the solution, where there is a equation. So there is a equation where V dc per dt plus QC equal QC, where C known as 0. So from table 3.1, there's a Laplace transform like this equation, Laplace df per dt equal sfs minus F. Since in the question V and Q are constant, so taking the Laplace transform like this. V Laplace dc per dt plus Q Laplace C equal Q Laplace C, where known C equals 0. So there is a equation that can conclude that SVC S plus QCS equal QCES. In the question, known that CT is exit concentration, so there are a requirement that CET equal O, F or T less than 0, and CT equal CE for T less than 0. Taking the Laplace transform of the input function a constant gives CE S equals CE per S. So substitution the equation 1, substitution this equation to equation 1. So there are equation that SVC S plus QCS equal QCES. So there so that can be SVCS plus QCS equal QCE per S. And then CECS times CV plus Q equal QCE per S. So CS equal QCE per SV plus Q times S. And then CS equal CE per VU S per key plus 1 times S. So from the table 3.1 pair 3 with torsi equal V per Q, we can get the Laplace transform like this. Like this equation. So the last equation that we can get is CT equals CE times 1 minus exp min Q per V times T. So if we using MATLAB with V equal 2 meter cubic, CE equal 50 kilogram per meter cubic, Q equal 0.4 meter cubic per minute, the result. Okay, closer.
What is the value of CT at times equal to 0? This is 0, right? Over here. Is that correct?
Yes, sir. Yes, sir.
Hmm?
Yes.
What is CT?
CT is
What is the capital C?
concentration.
Huh?
Concentration.
Concentration. Yeah, concentration what?
Concentration the inlet and exit.
Oh, I don't understand. There will be no inlet with this and outlet with the same notation.
The exit concentration, sir. I mean.
You have the exit concentration. Oh, okay. So the exit concentration will be 0. Is that what you're saying? At t equals to 0, the exit concentration is 0.
Where time is 0, so the exit concentration is 0 too, sir.
Okay.
So this is the graph of apa namanya, concentration, exit concentration vs time, like this, like that, sir.
Yeah, but there is no indication of exit concentration
Oh,
and no indication of time.
oh yes, sir.
So
Okay,
everyone can say anything about this graph.
okay, I'm sorry, sir.
Yeah. All right. Any other questions? No? Any questions from audience? Okay, now 19. Again, Risky,
Okay, sir.
number 19.
So this is the question of 3.19, where a liquid storage facility can be modeled by like this question, where Y is the liquid level and U is an inlet flow rate. Both are defined as deviation from the nominal steady state. So we can change this equation to be like this, yeah, to be like this equation. So from this equation, we can get the Laplace transform give like this: Laplace 2 quadrat y per dt quadrat plus 5 Laplace dy per dt plus Laplace yt equal 8 Laplace du per dt plus Laplace ut. From table 3.1, we can get equation 1 like this. So s quadrat ys minus sy 0 minus y accent 0 plus 5 sys minus y0 plus ys equal 8 cu minus u0 plus us. Now u0 equals 0 and y0 equals 0, y accent 0 equals 0. So from the equation 1, from this equation, we can get that s quad ys minus 0 minus 0 plus 5 sys minus 0 plus ys equal 8 SUS minus 0 ys plus ys equal 8 SUS plus US. YS times x quadrat plus 5s plus 1 equal US at s plus 1. When US equal 1 per s, so we can get that ys times s quadrat plus 5s plus 1 equal 8x plus s, and so we can get that ys equal 8s plus 1 per s times s quadrat plus 5s plus 1. Is my voice apa itu mantul?
And then you have to change into
Okay.
YT,
So
no?
yeah, yes sir. So from this we can factor the s quadrat plus 5s plus 1, and then we can get like this factor where f1 equal minus 5 plus square 5 quadrat minus 4 times 1 times 1 over 2 times 1, and s2 minus 5 minus square 5 quadrat minus 4 times 1 part 2 times 1. So we can get that s1 equal 5 minus 5 plus square 21 per 2, and S2 equal minus 5 minus square 21 per 2. Okay, so we can get that ys equal 8s plus 1 per s times s squared plus 5s plus 1. And then we can get the factor that we can get in book. So with s equal s plus 1 per s times s plus 5 minus square 21 per 2 and times s plus 5 plus x square 21 per 2. And then the equation became equation like this, where ys equal 8s plus 1 per x times s plus 5 minus square 21 per 2 and times s plus 5 plus square 21 per 2 equal a per s plus b per s plus 5 minus a square 21 per 2 plus c per s plus 5 plus square 21 per 2. Then we have to find a, find b, and find c. We can get like this. And then the equation 2 become ys equal 1 per s plus minus 21 plus 11 square 21 per 42 s plus 5 minus square 21 per 2 minus 1 per 42 plus s plus 5 plus square 21 per 2. And then ys equals 1 per s plus minus 21 plus 11 plus square 21 per 42 times 1 per s plus 5 minus square 21 per 2 minus 21 plus 11 square 21 per 42 times 1 per s plus 5 plus square 21 per 2. And then the Laplace s equal Laplace 1s plus minus 21 plus 11 square 21 per 42 liquid Laplace 1 per s plus 5 minus 21 per 2 minus 21 per s plus 5 plus square 21 per 2. And then yt equal 1 plus minus 21 plus 11 square 21 per 42 a square 21 minus 5 per 2t is 21 plus 11 square 21 per 42 minus 5 plus square 21 per 2t, and then we can get yt like this 42 per 42 minus 21 per 42 square 21 minus 5 per 2t plus 11 square 21 per 42 a square 21 minus 5 per 2t minus 21 per 42 minus 5 plus square 21 per 2t minus 11 square 21 per 42 minus 5 plus square 21 per 2t. And then we can, if we using MATLAB, we can write t like this, where this figure is weighty versus time.
Okay. Why don't okay? go back to hello.
Yes, sir.
Hello.
Yes, sir.
Go back to previous slide. Can you do that?
Hello. Excuse me, sir. It's like my bandwidth is slow.
Hello. Rizky.
Hello. Yes, sir. Yes, sir.
Oh, I see. Just for go to the previous slide. Okay.
Hello, sir.
Hello.
Yes.
Roll down.
Okay.
Yeah, stop here. Stop here.
Okay, sir.
Oh my goodness.
I'm sorry, sir. I think we can hear you clearly.
Oh, it's automatically down. And you now?
Yes, sir, but not
Can
clearly.
you?
Your voice is delayed.
Okay. Okay. Hmm. Oh. Oh. Hello.
Yes, sir.
Yes, sir.
Can you hear me?
Yes, sir. Yes, sir.
Okay. My question is, why you have to factorize this in the laptop as square? Okay. Minus hello. Hello, can you hear me?
Yes, sir.
Yes, sir.
Okay. My question is why you use s squared, why you factorize s squared plus 5s plus 1? You can use s squared plus 2.5s square minus 0.25 square in order to make this equal to 1. You can do that, right? So you don't have to factorize this. And then when you do like that, you can find from the table. Is it saying?
Yes, sir. I can get it.
Hello? Okay. That's my, yeah, okay, that's my question. Okay, well, anyway.
Yes, sir. I'm sorry,
Maybe
sir. I think
Rizky,
still
can you
delay.
stop screen?
Oh,
Think still delay.
Okay, can you see me now?
Yes, sir. Yes, sir.
Hello? Can you see? Okay, I'd like to discuss chapter 5, dynamic behavior of first order and second order processes. Can you hear me? No?
Yes, sir.
Okay. No, yeah. Radifan, can you hear me?
Yep, but I think still it is not like quite clear, sir. Like there is several delay or yeah.
Radifan?
Yes, sir. Maybe if I may suggest, you may turn off your camera to smooth the connection. Your camera to smooth the connection.
Okay. Yeah.
Yes, sir.
Amanda, can you hear me?
Yes, sir.
Okay. Jawo, can you
Yes, sir.
hear me?
Yes, sir.
Jawo?
Yes, sir. I can hear you, sir. Yes, sir. I can hear you, sir.
Okay, Radifan, is it better now? You can hear me clearly.
Yeah, I guess yes, sir.
Second order transfer function. So I have talk about the dynamic behavior for first order. So from equation 5.3, ys over k over tau s plus 1 us. So we would like to change us here in order to find the response of y. Process inputs is one is the step input. Okay, the step input has the function something like this. US is equal to 0 of okay, so that's what we have over here. Okay, US is equal to M over S. For RAM input, UT is equal to 0 at t less than. This is the function of t, and the and the Laplace transform for u for the rectangular pulse us will be equal to h over s 1 minus EWS. Okay. Right, because we have h here, so if h is equal to 10, of course this is going to be 10. Okay, 11. So we have what's the for example, for the rectangular pulse we have let me see. One time I told you you have two step inputs, okay? One starting from t equals 0 and the other from t equals to tw. However, in here, Seberg says he has two inputs also. One is the step input, and but in the negative side. Okay. However, when we add up this together, it will be like this. Okay, the same thing if we have two step inputs. Okay, but we subtract one input to the other. Okay. Again, this is the rectangular pulse input. Okay. I think this is the most important input. Oh, the other one is sinusoidal input. Okay, where for the sinusoidal input is the when t equals 0, ut is equal to a sine omega t. Okay, and the us will be this one. US, if we look at the table, will be a times omega over s squared plus omega squared. Okay. And we also have the impulse inputs and the random inputs. Well, I don't want to talk about that. Just the 3 inputs. The 4 input includes the sign function, okay, which is more important in this course. Okay. For a step input of m, and ys will be equal to km over s tau s plus 1, and using table 3.1, yt will be equal to km 1 minus e to the minus t over tau. And we have to plot something like this, okay? And this is the behavior of first order system, okay? Whereas when t equals to tau, the output will reach 63.2% or 0.632 of the final result. Okay, so this is the characteristic of first order process. Okay, when t equals to tau, then the output will reach 0.632 of the final output. Okay, and the derivative at t equals to 0 is equal to 1. Okay, so if you put a straight line from here to here, then you get the value, you know, for the derivative for y over km with respect to t over tau in here. This is will be equal to 1. Okay, and normalized response of a first order process to step input. So at t equals to tau will be equal to 63.21, and when t equals to 5 times tau, it will be equal to 99.33% of the final result. Okay, final value of the output. Okay, and this is the example 5.1. Just you know, put the values in the equation, and you will see the numerical values. Okay, so I don't want to discuss about it. You can also find over here. Now for the RAM response, okay, so what you have here, if us is a times t, and we have ys something like this, okay, because us will be equal to a over s squared, and you will have yt is equal to such as equation 520. Okay, when t greater than tau, then yt will be equal to kat minus tau. Okay, so when you try to draw the function, you will have, this is the input ut over a, and this is the output yt over ka. And we subtract this together. Okay, this is going to be a parallel line. Okay. Hello, can you hear me?
Yes.
Okay. See, you have this is a parallel line. Okay, so when t goes to infinity, what happens is you will have on a straight line over here. Okay, you will have a straight line, okay, with a slope of what KA. Okay. So that's the ramp response, and well, I will have to stop here. For the sine function, it's going to be different. There is a lot that to have to be discussed for ramp sinus. Okay, sinus response. Okay, I will discuss it next week for sine response. Any other questions? Is there any questions up to chapter 5 here? 522 ramp response and step response. Do you have any questions? No?
No, sir.
Not yet, sir.
Not yet. Okay. All right. I think I will resume up to this point. Please read chapter 5. Okay. For next week, we will discuss chapter 5 next week. Okay. There is no assignment other than you have to read chapter 5. Okay.
Okay, sir.
Okay, sir.
Yeah. All right. I'll see you next week. Thank you.
Okay, thank you.
Thank you, sir.